Okay, welcome back. Okay, so now one thing I want to state before we go into this example is that when we look at homomorphisms and we drop, because we drop that one-to-oneness, we lose the perfect correspondence that we had going from domain to range. But what we retain is this idea, the likeness of the range to the domain, or this analogous relationship. Okay, so as we go through this example here, keep that in mind. So for example, we think of R3 as like R2, right, in a way, except that the vectors have an extra component, right? So they're vectors, right? So in 3D, right, three-dimensional versus two-dimensional vectors. So the only difference is that the vector components are x, y, and z in R3, but of course we lose the z component and we just have x and y in R2. Okay, so this is what we have with the projection, right? The pi function. Now, defining the projection map pi makes precise which members of the domain we are thinking of as related, related to which members of the codomain. Okay. Now, we look at some of these things as we go forward. One of the things that we want to think about or understand is how the preservation conditions in the definition of homomorphism show that the domain elements are like the codomain elements. And we start by picturing R2 as the xy plane inside of R3. Okay, in other words, the xy plane inside R3 is a set of three tall vectors with a third component of 0. You can think of it that way too, right? So the third component is just a 0 component. And so it does not precisely equal the set of two tall vectors in R2, but this embedding makes the picture much clearer. Now, the preservation of addition properties say that the vectors in R3 act like, in other words, the shadows of R3. Okay, or shadows in the plane. Okay, so here, if we look at this, like for example, when we talk about addition and we'll talk about scalar multiplication too. And again, my drawings aren't the best, but if we say have this vector here, x1, y1, z1, right? That's its shadow, which is going to be right above x1, right? That's going to have a projection. And then we have this other vector that's way over on this side here, x2, y2, z2 is going to be above this vector x2, y2, right? That's on the floor, if you will. And then this one is the addition of these two, right? So what this is showing is that addition is preserved, because if we add up the vectors in 3 space, it is the same, or, well, analogous to adding up their shadows, right? I mean, you're not going to get the exact same, obviously it's 2 space, but the addition is preserved. So the shadows add up, or what am I trying to say? That the shadows preserve addition. Now, thinking of the projection pi as the shadow of the vector v, like if we do pi of v is the shadow of the vector v in the plane, gives this restatement of the sum, so that the sum of the pi's is equal to the shadow of the sum, which is pi times the sum of the vectors. So the sum of the pi's is equal to the pi of the sum, is what we're trying to say. Okay. I think that's all I want to say on this. So we're going to go more into this as well, and that's going to be important. So, okay. Have a great day.